Hello students, in this video we'll discuss how to construct a confidence interval for the difference of two population means. Let's suppose that x1, xn are normal, are samples of a normal mu x sigma x squared random variable. And here I'm going to assume that sigma x squared is known, where the variance over here is a known quantity and this mu x is unknown. Okay? And similarly, I'm going to let y1 through ym be samples of a normal mu y sigma y squared random variable, where the sigma y is known, so you know the variance, and you don't know the mean, unknown. Okay? Then I'd like to find a confidence interval. Let's find a confidence interval, let's say 95% for standardization. For mu x minus mu y. Okay? And so the idea is we're going to use the normal distribution, right? And so our normal distribution looks like this. That's a standard normal distribution. There's x, and then there's going to be the f of x axis, and this is standard normal, so this is going to be 1 over the square root of 2 pi e to the negative x squared over 2. Okay? And I know that if I want a 95% confidence interval, I have to be in some acceptance regions. I'm going to make it symmetric. So I'm going to pick a point over here and a point over here, right? And if that point happens to be 1.96 and that point is negative 1.96, then I know that 2.5% of the probability is over here, 2.5% of the mass is over here, and then over here, on this tail over here, 2.5% is over here, which means there's 95% chance that you're in this sweet spot region over here. So there's a 95% probability that you're over here in this sweet spot. That region over there is 95% of the mass of the distribution, okay? And so what I want to do now is I want to look for an estimator, and so what I'm going to do is I'm going to use a natural choice for an estimator. What I'm going to do is I'm going to consider x bar, the sample mean. X bar is just going to be x1 plus all the way down to xn over n. Then I know the expected value of x bar is just going to be mu x, and the variance of x bar is going to be sigma x squared over n, sigma x squared over n. And then likewise for the sample mean of y bar is going to be y1 plus all the way down to yn, m now, all divided by m. Now in this case, the expected value of y bar is going to be mu y, and the variance of y bar is going to be sigma y squared over m. Now at this point, I'm going to make another assumption. I'm going to assume now, to make this problem nice and easy, that the samples x1 through xn and y1 through ym, I want these to be independent of each other. I want the samples to be independent. Okay? And now what I'll do is I'm going to look at this estimator over here. So now I can look at this thing. Let's consider, if we look at x bar minus y bar, this will have mean, has mean. Well, it's the mean of x minus the mean, x bar minus mean of y bar, so it's going to have mean mu x minus mu y. And what's the variance of this thing over here, or the standard deviation, has standard deviation? Square root of sigma x squared over n plus sigma y squared over m, because they're independent, okay? And so now this thing actually has a mean of this, and this also has x bar minus y bar is normally distributed. Because the sum of independent normal distributions is still normal. That's an important feature of this. And so now I can form a test statistic from this. And so what we're going to do is we're going to form x bar minus y bar minus mu x minus mu y over the variance of this thing, sigma x squared over n plus sigma y squared over m. This is a normal 0, 1 distribution, okay? And so what can I say now? So I can use the fact now that the probability that this, if we call this variable over here z, the probability that z is between negative 1.96 less than z less than 1.96 is equal to 0.95 by our graph over here from our standard normal. And so now we can construct the confidence interval, right? And so now the confidence interval for this thing, so our confidence interval, our 95% confidence interval, is going to be what? Is going to be x bar minus y bar plus or minus 1.96 times the square root of this times the variance over here. So that's going to be sigma x squared over n plus sigma y squared over m. And that's our confidence interval. Now, if I wanted to adjust this to be a difference confidence interval over here, if I want to say, for example, a 100 1 minus alpha over here, if you wanted a 100 1 minus alpha confidence interval over here, then what you would need to do is you would need to look at this number over here, this, let's call this number over here z alpha over 2, and this number over here negative z alpha over 2, where the probability that you're past this point over here, where that probability would be alpha over 2. And that probability over here, on the other side over here, would be alpha over 2. And then you just replace this 1.96 with that z alpha, that z score, that z alpha over 2, and that will give you a different level of a confidence interval. Thank you very much.